Hi dear students. Now we'll move on to the next topic, integrated rate equation for a first order reaction. So in the previous video, we have seen how to integrate a zero order reaction. So we'll be extending the same to a first order reaction also. Now we'll begin with the calculations or the integration. Now listen. Now let us consider a first order reaction R giving P. Okay, now you consider a first order reaction. Okay, a first order reaction. So let the reaction be R giving P. R giving P. So we have the instantaneous rate. The instantaneous rate of this reaction will be rate is equal to minus dr divided by dt. Yeah, because R is the reactant, so the instantaneous rate will be minus dr by dt. And also we have the rate equation. The rate to law, rate is equal to K into concentration of R raised to 1. Previous case is 0 order, it is R raised to 0, but this is a first order reaction, so we can write it as K into R raised to 1. So let this be equation 1 and we call this as equation 2. And on comparing equation 1 and 2, when you compare equation 1 and 2, you can see that both represents the rate. So I can write minus dr by dt, that's equal to K into R raised to 1. You can do along with me. Okay, now take a paper and try to do these integrations. So you got minus dr by dt is equal to kr. Now we need to integrate that one, and before integration we'll make some rearrangements. So on rearranging I can write minus dr by r. Okay, minus dr by r is equal to k into dt. Or I can say that dr by r is equal to minus k into dt. dr by r is equal to minus k into dt. We call it as equation 3. Next step, let us integrate this equation. On integrating this equation, we'll get integral dr by r. That is equal to minus k into integral dt. Minus k into integral dt. Clear? So we know that what is integral dx by x? You know that integral dx by x is equal to natural logarithm of x. So this can be written as natural logarithm of r. Layer. That will be a constant, will be there. Constant will write at the last. Okay, that means that is equal to minus k. And what is integral dt? Integral dt will be t minus kt plus c. So let this be equation 4. Now what we have to do? We need to find what should be the value of C. In order to find the value of C, now here R is the concentration of reactant at time t. And when t is equal to 0, now to find the value of C, okay, find the value of C, we'll substitute when t is equal to 0. When t becomes 0, R will be equal to the initial concentration R0. We call that R0 as the initial concentration. Because in the previous class also I have told you, at time 0 means initial time, means that will be the initial concentration of the reactant. And when time becomes like t, so when 0 time, when the reaction starts and reaches a particular point, the concentration of reactant becomes R. So here, I can now listen once again. Now this is the time 0. Let the concentration of reactant is R0. Now at time t, concentration of R is written as R. So here this R represents the concentration of reactant at time tn. And if time t becomes 0, when time t becomes 0, R will be equal to initial concentration. Because time changes means the concentration also changes. So when time becomes the initial time, when you consider it as the initial time, then the concentration of reactant will be R0. Hope it is clear. Now we'll continue with the derivation. Okay. So I can write natural logarithm of R. Natural logarithm of R is equal to minus k into 0 plus c. Because when time becomes 0, that means the natural logarithm of R0. Okay, not R, that will be R0. That means here the value of R changes to R0 and you'll get c is equal to, therefore c is equal to natural logarithm of R0. Now we'll substitute the value of C in equation 4. Substituting the value of C in equation 4, we'll get natural logarithm of R is equal to minus kt plus natural logarithm of r0. Natural logarithm of r is equal to minus kt plus natural logarithm of r0. And this equation is called integrated rate equation for a first order reaction. Integrated rate equation for a first order reaction. So natural logarithm of r is equal to minus kt plus natural logarithm of r0. And now you can see that this equation is of the form y equal to mx plus c. So I'll write natural logarithm of r is equal to natural logarithm of r0 plus minus kt. Minus kt plus natural logarithm of r0. So comparing this equation with y equal to mx plus c. Now if you try to plot the graph, see on the y coordinate, you should have natural logarithm of r. You'll be writing natural logarithm of r versus time t. Okay, wow. So that you'll get a straight line with a negative slope. So minus k will be the value of slope. So the straight line will be like this. Okay, so the value of slope will be equal to natural logarithm of r0. The y-intercept is equal to, not the value of slope, the y-intercept is equal to natural logarithm of r0. And what is the value of slope? Slope is equal to minus k. So we have got the equation natural logarithm of r equal to minus kt plus ln r0. And this will be the graphical representation. Okay. Now again, we'll go for a further derivation. We'll not stop the derivation here. And as I told, this equation is called integrated rate equation for a first order reaction. Okay, wow. Now we'll make some rearrangements. Now listen here. Natural logarithm of r equal to minus kt plus natural logarithm of r0. So here I can write natural logarithm of r minus natural logarithm of r0 is equal to minus kt, or natural, this is log a minus log b, which I can write it as natural logarithm of r by r0, that is equal to minus kt. Now if you take anti-log on both the sides, we'll get r by r0. R by r0 is equal to e raised to minus kt. And therefore r is equal to r0 into e raised to minus kt. So this is the next equation. Concentration of r is equal to r0 into e raised to minus kt. So here we are taking the anti-log. Okay, anti-log of natural logarithm of r by r0 will be r by r0 itself, and anti-log of minus kt will be e raised to minus kt. So we got an equation r equal to r0 minus kt. Sorry, r0 into e raised to minus kt. Again, now listen, we'll continue with this equation. So you got minus kt equal to so we'll continue with this equation. Okay, we'll continue with this particular equation. So once again, another equation we'll move on to. Listen here. So we'll move on to, so natural logarithm of r equal to minus kt plus natural logarithm of r0. So we'll continue with the derivation. So we'll get natural logarithm of or kt is equal to natural logarithm of r0 minus natural logarithm of r, or kt is equal to natural logarithm of r0 divided by r, or kt, that is equal to 2.303 log r0 divided by r. So we get kt is equal to 2.303 log r0 by r, or k is equal to 2.303 divided by t log r0 divided by r. So we'll be using this equation to calculate the rate constant for a first order reaction. The rate constant for a first order reaction, k is equal to 2.303 divided by t. Okay, this is t divided by t log r0 divided by r. This equation can also be written as k is equal to, listen, k is equal to 2.303 divided by t log a divided by a minus x. Okay, wow. log A divided by A minus X, where A represents the initial concentration of the reactant. This A represents the initial concentration of the reactant, and A minus X represents the concentration of reactant at time t. If R0, this R0 represents the initial concentration of reactant, and R represents the concentration of reactant at time t. So here R0 means A and R means A minus X. Then what will be X? Here the X represents the amount of substance that is reacted by time t. Okay, wow. So X is the amount of substance reacted, A minus X is the remaining substance at time t. So this is the amount of unreacted substance. A minus X means the amount of unreacted substance at time t, or we can say that the concentration of reactant at time t. Now at T1, at time T1, let the concentration of reactant, let it be R1. And at time T2, let the concentration of reactant, let it be R2. So let R1 and R2, be the concentration of reactant at time T1 and T2. Then we can write K equal to 2.303 divided by T2 minus T1 into log concentration of R1 divided by concentration of R2. So at time T1, so this is the value of rate constants at different time intervals. So K is equal to 2.303 divided by T2 minus T1 log R1 by R2, where R1 is the concentration of reactant. R1 is the concentration of the reactant at time T1, and R2 is the concentration of the reactant at time T2. And now if you take this equation, okay, K is equal to 2.303 log R0 by R. Now listen, K is equal to 2.303 divided by T log R0 by R dane. So we'll make some rearrangements. Okay, now get ready. So this is very interesting. Okay, now log R0 by R. Now listen, log R0 divided by R. I'll write it as K divided by 2.303 into T. That is equal to KT divided by 2.303. And if I say this equation is of the form y equal to mx plus c, will you agree with me? Now what will be the value of c? Because you have y will be representing log R0 by R, k by 2.303 represents the slope, the t represents x. Then what is c here? Now, yes, that's it. Now the value of c that will be taken as, we have to consider it as 0. So this equation is of the form log R0 by R equal to k by 2.303 into t plus 0 is of the form y equal to mx plus c. Now if you plot the graph, for this equation, if you try to plot the graph for this equation, see now listen here, the value of y or then the y-axis, you should have log R0 by R, okay, log R0 by R on the y-axis, log R0 divided by R will be there on y-axis. So this is the y-axis. Then you should have time on the x-axis, t. So you'll get a straight line with y-intercept 0 dane. Y-intercept 0 means the straight line should pass through the origin. And here the value of slope, so the value of slope is equal to k divided by 2.303. K divided by 2.303. The value of slope will be equal to k divided by 2.303 for a first order reaction. So if for log R0 versus R, versus time, log R0 by R versus time, the value of k is equal to slope into 2.303. The value of k will be equal to slope into 2.303. So remember all these equations. Okay. Now we'll move on to some of the examples for a first order reaction. Now listen. Examples. Okay. Now we'll move on to few examples for a first order reaction. Okay. Now examples for first order reaction. Now if you take the first example is hydrogenation of ethene. Hydrogenation of ethene. So the reaction will be C2H4. Okay, C2H4 plus H2 giving C2H6. So what will be the rate equation? The rate equation will be rate is equal to K into concentration of C2H4 because it is a first order reaction, C2H4 raised to 1. That means hydrogen will not be involved in that rate equation. Another example is, this is very important, all natural and artificial radioactive decay. All natural and artificial radioactive, radioactive decay. All natural and artificial radioactive decay will be an example for a first order reaction. So suppose if you are provided with during a nuclear explosion. During a nuclear explosion means that will be a first order. So you have a question in NCERT, we'll be discussing it. So it will be mentioned as during a nuclear explosion means you have to consider it as a first order reaction. Okay, wow. So we'll take one example now already. So one of the example given will be like if you take the case of radium. Okay, our radium like 22688. So on radioactive reaction produces helium 42 along with radon 222 and 86. Okay, radon 222 and 86. So this is an example for a first order reaction. Then another reaction, decomposition of N2O5 decomposition of N2O5 and also decomposition of N2 and N2O. All these are example for first order reaction. So in this case, in radioactive disintegration, I can write rate is equal to K into concentration of radium raised to 1. So this is very important example. Okay, that means all natural and radioactive decay are also examples for first order reaction. So hope it is clear. Now see that we'll move on to the derivations. You can see. So integrated rate equation for a first order reaction. So these are the calculation, and we have seen the graphical representation also. So here the value will be equal to KT equal to 2.303 log R0 divided by R, where R0 or A0 means initial concentration. Okay, so I have mentioned like R0 by log R0 divided by RR. So log R0 by R, that will be equal to R0 represents the initial concentration and R represents the concentration at time t. This also can be written as log A divided by A minus X. Okay, log A divided. So A represents the initial concentration and A minus X represents the concentration at time t. Okay. Now go through the equations and study that. That means you have to study the value of K for a first order reaction and also for a zero order reaction. Okay, so zero order reaction, K is equal to R0 minus R divided by T, and for a first order reaction, K is equal to 2.303 divided by T log R0 by R. Okay, so hope this session is clear.